Hello everyone, my name is Adrian and today I'm going to talk to you all about the igneous rocks of the Troodos Mountains in Cyprus. I just want to mention before we get started that at the top left of the screen, you'll sometimes see bolded text that says refer to the lectures so-and-so, and this pretty much means that any of the bolded text you see in the slides are terms that we have already gone over in class. I put it there in case any of you wanted to pause the video and go to said lecture to refresh your memory to remind yourself of those terms and what I might be referring to. I also want to say that the virtual background isn't working for me for some reason, so I have to do it like this in order to get my face actually in the recording. So now that we get that settled, let's get into it. So these mountains can be referred to as the Troodos Massif and or Troodos Ophiolite. In text, they're pretty much referring to the same thing, since the ophiolite sequence is just oceanic crust brought up to the surface and then uplifted into what we now see as mountains, aka the Troodos Massif. And you see that in the background. So this ophiolite is said to be one of the best preserved ophiolites in the world, and we could find a great deal of igneous rocks here. For example, we see mantle peridotite, felsic to intermediate plutonics, sheeted dikes, and pillow lavas. And they all give us a clue into the composition of the oceanic crust and upper mantle from those times. So this ophiolite spans about 3,000 kilometers squared. And if you see in this image below me, in the bottom right corner, that's pretty big compared to the island of Cyprus. It's also said to be around 90 to 92 million years old, and that's referring to the rocks, and it's said to have formed as a supersubduction zone rather than a mid-ocean ridge. So I know we haven't really gone over what that is, so if you don't know what it is, then I'll quickly explain it to you, and don't worry, I had to do a bit of research myself to figure out what it meant. So a supersubduction zone is pretty much what you see in the image on the right here. I'll quickly, When we say supersubduction zone ophiolite, we pretty much are focusing more on its geochemistry and how it is similar to what we find at island arcs, but it formed through seafloor spreading right above subducting oceanic lithosphere. I know it's really strange and I'm still a bit unsure about it myself. So don't worry if you're confused about that part because it isn't super critical to what we're going to be talking about. So the highest point of this massif is known as Mount Olympus. My guess is that it's in reference with the Mount Olympus of Greek mythology. It's crazy to imagine, but Mount Olympus is actually used to be one of the deepest parts of this entire ophiolite sequence. As to when and how it was uplifted to that high point is still not fully understood. So the image to the right, the blue diagram, that is Mount Olympus. The entire body is mantle peridotite, and it could be split up into the U1 Harzbergite and U2 Harzbergite units. This was done based on their compositions. The Harzbergite body of U1 is said to be within a spinel and have high concentrations of olivine and orthopyroxene, all interlaid between dunite bodies. And those dunite bodies can be seen in black, in the blue diagram. So researchers believe that these bodies were formed through the fractional crystallization of a bonanitic melt constantly being replenished by depleted magma source. And we could see that process on the left image there. So in that magma chamber, we have a dunite and lherzolite / Harzbergite body, okay? A layer. So new melt from a depleted source will inject and fill up the chamber and mix with the melt that's already in there. This newly mixed melt will then fractionate and form more layers of dunite and then lherzolite / Harzbergite, and then eventually become exposed to the surface and seen as the U1 and U2 bodies. Other researchers thought that these zones were actually formed through a reaction between spinel lherzolite and other melts that are closer to the surface. To be honest though, I believe that both processes can still exist and form these bodies, but they just occurred at different times. For example, the bonanitic chamber just went empty, and then the other process replaced it and formed the rest of the unit. But that's just for the U1 body. The U2 Harzbergite has barely any clinopyroxene, and this is actually how they differentiated from U1. Some researchers think that these formed from an open system reaction between an initial spinel lherzolite and infiltrating melts. It probably didn't undergo the same process of formation as the other one, but still much more straightforward. So I mentioned before that we were still a bit unsure as to how ultramafics of Mount Olympus got all the way up there. One theory people had was that it was uplifted through what is called serpentinite diaparism. We also see some gabbros in the area too. So in the yellow, in the diagram on the bottom right, you see in the yellow, that is the gabbro, and it's surrounding the ultramafic rocks. So that's what I'm referring to. And these are made up of the two types of pyroxene, clinol and ortho, and as well as plagioclase. And then the distribution between pyroxene and plagioclase is like a 50-50 split. So the reason why they thought it was through serpentinized diaparism was mostly because of the serpentinization that they see in the ultramafics and like some of the gabbros. So to see if this was actually possible, they used the Mariana margin as an example and realized that buoyancy would be a driving force to uplift the blocks and take them all the way up there. So they found that the buoyancy force in Troodos, well, they estimated, would be enough to only uplift the ultramafics, but nothing else. Again, though, this is just a theory based on one margin boundary, and there could be other factors at play that could have uplifted the rest of the massif through serpentinite diaparism or a completely different process too. So now we have the felsic intrusions. It's odd to think that felsic intrusions are found within oceanic crust. That's mostly mafic, but they do exist, and we call them oceanic plagiogranites. In the image on the right, you could see that the plagiogranite intrusions are in red around Mount Olympus, and you also see 3 different groups. So these groups were divvied up based on their geochemistry and incompatible trace element compositions. The main group is thought to have fractionally crystallized from a thalliatic melt, which actually also forms much of the lavas and sheeted dikes around the ophiolite. The second group, the spileo group, is believed to come from a bonanitic melt, while the third group, the Zupigi group, is termed as the group that has no genetic relationship to any other rock in the ophiolite sequence. And that's all there is to say about that one. However, the actual fractionation process is thought to take place in a shallow magma lens that is water unsaturated, and through the partial melting of hydrothermally altered crust too. So that only covers the ultramafics, the gabbros, and the felsic rocks, but we still haven't gone over the upper and lower pillow lavas or the Aracapas fault belt. So many of the primitive rocks in this ophiolite are found among the upper pillow lavas in the Aracapas fault belt. These rocks are mostly composed of your phosphoric olivine with an augite ground mass and may or may not have some enstatite. Aside from primitive rocks, we can identify 3 different types of primitive lavas. And this is similar to the other bionic chamber where we talked about for the Mount Olympus. These primitive lavas are believed to have formed from the incremental melting of a depleted magma source. So one of these groups is a thalliatic basaltic to rhyolitic lava that is also parental to the lower pillow lavas. The second group is said to be a picritic and thalliatic basaltic to andesitic lava that is parental to the upper pillow lavas. And then the third group is simply just a bonanitic lava and is parental to the Aracapas fault belt. And that's the end of my presentation. I'd like to thank you all for taking the time to watch it, and I hope you got more insight as to what the Troodos Massif / ophiolite is all about. I wish you all luck in your future studies and your exams, and I hope we all get to meet each other in person next year. Have a good summer, everyone.